Dear all, welcome to this new episode of CATIA Talk for Buildings and Infrastructure on Small and Modular Reactors with our subject matter experts, Robert PESUT. A small and modular reactor, an SMR, is a type of nuclear fission reactor that is smaller in size and output compared to traditional nuclear reactors. SMRs typically generate up to 300 megawatts, while conventional reactors have capacities of around 1,000 megawatts or more. SMRs are designed to be modular, meaning they can be assembled off-site and then transported to the final location for installation. This modularity can help reduce construction times and costs compared to traditional large-scale reactors. When developing an SMR, the need is important of using a complete and integrated platform to provide the owner and the operator with the right tools to deliver and operate the asset on time and on budget, while sustainably less risks. Using this virtual twin enable multidisciplinary collaborative virtual modeling and simulation of complex buildings and facilities, the performance and behavior as well as its schematics. This CATIA talk will be held here in the post, where you are, on the CATIA Buildings and Infrastructure community, but also in our YouTube channel and in our LinkedIn channel. So don't hesitate to rewatch the webinar, attend and promote this webinar to your business ecosystem. Thank you very much and have an excellent day.
Hello everyone and welcome to the show for the SMRs or Small Modular Reactors with the CATIA. Today's topic will be, again, how we did the SMR on the MBSC and the CATIA part. So just a brief introduction. We will be covering a couple of main topics. General introduction on the SMR for the very beginning with a couple of items from the engineering excellence. We will follow that with accelerating advanced nuclear technology programs and finally going on the SMRs for the CATIA. So virtual twin for the SMR engineering, we will have a couple of use cases. So actually 2 use cases because we will be covering the SMRs for 2 different geolocations, taking a look on the overview of that, and finally on the end, the virtual twin values for the SMRs. A little bit on the coverage that we're going to cover today is, so with the solution for the asset lifecycle management, we can cover the entire lifecycle of the project, starting from the new project or the bidding phase up to the decommissioning. What we will take a look today is a little bit of the basic design and conceptual design with CATIA Magic or the MBAC, 3D design, and the construction phase is focusing more on the piping and the construction for within the CATIA. A couple of items for the very beginning. So the engineering excellence within the CATIA from I&M or infrastructure, energy, and materials industry that we'll be covering is the conceptual plan design. So pushing inside all of the requirements, plan design, so basic and the detailed design, pushing in the specifications, playing with the specifications, extracting the requirements from the conceptual plan design phase and driving the design with those requirements. The next phase is multidisciplinary design review, where we can generate a fully integrated and functional digital mockup covering all disciplines, all stages, and covering the entire life cycle. And finally, coming to the plant performance and integrity assessment, where we are covering some simulations, 1D, 2D, 3D simulations based on the requirements that we can also reuse the outputs later on to create a couple of iterations of those simulations and improve our design. Today, you're going to hear a lot about the RFLP, which stands for the requirements, functional, logical, and the physical. On the requirement side, we are consuming all of the requirements that are related for the project, whether they are the engineering or non-engineering requirements that are driving the design. Functional part is covering the conceptual design of the systems. Logical, the systems themselves, whether we're talking about the BFD, PFD, or the PNID. and the engineering or the physical is covering the digital representation of our logical functions. Throughout the entire life cycle, we can perform a certain set of the analysis, 1D, 2D, 3D, as mentioned before, and we can also consume a certain outputs from the different software vendors, like the standards ISO 59226, ISO 1033, IFC as the main exchange format, and the IGES as the format for the equipments as well as the step. Throughout the phases that we saw just before, there is a number of disciplines that can be covered. Of course, we are not going to go through all of them. Just to mention the most important ones, we will be covering the requirements management. So again, consuming all of the requirements from the technical and non-technical documentation that are essential for the project. Safety, system safety analysis, also important, especially for the SMRs. A lot of requirements covering from the government, from the engineering departments and the disciplines related to the safety and to the core itself. PNIDs, 3D, CATIA data import, exchange management, virtual commissioning, so making a real simulation out of the systems that we finally built here. On the advanced nuclear technology programs, the most important key takeaways that are mentioned here are architectural challenges, because we're talking about the site, time to market to decrease the time on delivering the SMR to the market regarding the rapid growth of the electrical consumption, consideration of the entire nuclear life cycle, so taking care of the nuclear waste and pushing in the nuclear material within the SMRs, modularity and product line management, because we will need to reuse the same project regarding the requirements on the different stages. Life cycle, of course, how can I take into account the complete life cycle of my facility in the design? And finally, safety and licensing, can I really secure the regulatory program from standard design approval to license to operate? So a virtual twin is a key asset to address these challenges. And the life cycle of the SMR, in this case, it's demonstrating also on the big nuclear reactors, is building a virtual twin, safety analysis as a key point, and the requirements coming from the safety analysis that can drive our design later on. MBAC, or model-based system engineering, we will see here how the MBAC is basically evaluating our design later on, how we can consume the outputs. General arrangement, virtual twin, the terrain or the geolocation, factory and supply network for the virtual twin. So all of those are taken into account when we're designing the SMRs. As the backbone, mentioned before, but the key takeaway here, so giving life, this is a robust skeleton of fundamental processes. And why fundamental? Because there are standardized processes in other sectors, specificities of the NI to be considered, need for the development applications. So this is why the synergy makes sense. All of this within one platform, within one core. And all of this talking in between, creating a certain links that the users can later on relate to. So while these processes are standard engineering processes, there are also specificities that needs to be reconsidered, especially on the safety analysis. That's why it's highlighted here. And the never-ending process of designing a virtual twin. So we are not starting at a certain point. We can start at any point of the virtual twin here. Requirements are the baseline, and they are driving our design, whether we're talking about the 2D or the 3D simulation. We are building our digital twin from the 2D, building the skeleton, creating the 3D mockup, taking into account all of the items that we got from the subcontractors, suppliers, or the internal ones, performing different studies like the safety and hazard studies, multiphysics behavior, making simulation, 2D, 3D simulation on the systems that we designed, and also the outputs of the simulation shared with the local authorities, with the departments, with the suppliers, subcontractors. This will be the basic of the digital twin that we have, fully designed within the CATIA, geolocated, and taking into account disciplines like the piping, HVAC, electrical, and the buildings. The entire facility or plant in this case is built within the CATIA, and all of the simulations are performed within the certain apps that we have within the platform. The system of the piping is based on the certain specification. Couple of specifications can be pushed inside to drive the design. All of the fittings and all of the equipment that is placed here is also driven by that specification. On the end, a certain analysis can be performed on this 3D model, but before we constructed the 3D part, there is also a PFD and the PNID in the background that is driving this 3D design. So every single object that is here has its own 3D representation, and all of the reports and the outputs, deliverables that can be extracted from the model are extracted from both the 2D and 3D design. In our case, we are going to cover two use cases. The first one, building virtual twin of the SMR for a couple of markets. In the first case, it will be addressed to the French market based on the French regulations. On the second use case, it will be adapted to a different market with different requirements. Because as an architect, I want to understand the impact of adapting the current SMR to the new market. And basically, this is the baseline on the use case number one, how we built a virtual twin for the SMR. Everything started with the specification, all of the needs, life cycle, stakeholders, standards, and the requirements, specifications. Everything was driving later on either the process flow or some risk assessments that we had in the background and the reports that we had to send the outputs to the authorities. When focusing on the process flow, 0D, 1D, as I said before, PNID design and the simulation, space allocations, pushing the equipment inside, creating the connection between the equipments according to the certain specification, in this case for the French market, making certain simulations and the outputs of those simulations, driving it back on the requirements, and creating a couple of iterations with those simulations. Everything was followed with probabilistic risk assessment because of the safety and the hazard, and on the end it was combined within the digital mockup, so virtual twin simulation. This was also wrapped up as a safety case for a physical prototype and the authorization because a couple of authorities, classification societies, governments were included inside to make sure that everything is built according to regulation and could sustain a lot of hazards and can be operated within years and years to come. As we performed the design on the SMR, the same can be performed on the big reactors, so it's a scalable, definitely. Multi-physics structural analysis for the buildings, collaboration around 4D planning, where the material is going to come, what can be excavated, what is the requirement of the geolocation, what is the requirement of the equipment itself, how to maintain that equipment, how to maintain a periodical activities on the maintenance for the specific equipment, for the suppliers to bring the new equipment to go into the service departments, and all of that combined within the 3D experience virtual twin. And finally, taking into account the structural part as the baseline where all of our equipment is going to be stored in, We see in the background the geolocation or the scan of the specific area where we are positioning the plant. Geolocated site can bring its own requirements inside the requirements section, and can also have an impact on the systems, like in this case the cooling system for the SMRs. The building itself is being built according to heavy regulations and requirements for the seismic activities, and of course all of the floors, key areas are built according to those requirements as well. A couple of items taken from the building 3D design. So in this case, we can specify a certain template, either for the floor, for the concrete, the composition of the concrete, so the material itself, perform a certain analysis on top of that, and reuse that because once the template is being built, then that template can be reused for a different project. With the different projects come the different requirements. In that case, we can push those requirements in and make small modifications, not to redo everything from scratch. In this case, we are taking into account the precast module for the reactor core itself, with a certain set of the rebars, the number of rebars, the type, the concrete, the size, all of the parameters that are stored within the platform can be extracted and can be later on reused, and will be reused for a different project, for a different configuration. Extracting a couple of drawings, so basically every information that is stored in the 3D can be extracted, can be automatized to create the outputs and pushed as a deliverable for any type that we have for the project. Same is applied on the 3D simulation. So in this case, with the Simulia, we are creating the simulation for the specific pipe because of the vibrations, to make sure that everything will be according to the regulations. Output of that can be used to modify the design, to optimize it, and of course to reuse it later on. The output can be the virtual, so in this case the colored one, or extracted as the report if we want to use it as the official report for the authorities and the rest of the engineering department. Making the next step on the use case number 2. So we need to adapt this existing SMR to the new market. As I said, new market comes with the new requirements. New requirements can drive the design, and we don't need to reuse all of those requirements for the design itself later on. The product is configurable, so either one small piece or the entire product can be used as the template and adjusted for the new market. In this case, we're just taking one small piece out of the configuration, which is again the cooling system. Again, a different market with different conditions will require some additional stuff that needs to be pushed inside. And the product in this case is managed throughout the entire project dimensions. So new requirements are defining the new system architecture done with the CATIA magic. Product breakdown structure is defining some additional stuff that are pushed inside, because we're talking about the PFD and the PNID. As every 2D object has its own 3D representation and has its own space allocation. So we are having additional modules on the site, which is a space allocation, the equipment, assembly plan, and the manufacturing plan. So as you see here, one small modification, one additional configuration of the product can have the traceability, the changes on the entire life cycle of the plant itself. We'll be taking two items as the baseline here. The first one is the system architecture focus and the system engineering focus. On the architectural side, new requirement will have the impact on the architectural modules for certain decisions to be made. And on the system engineering side, we're going to have, of course, 2D, 3D, certain simulations, GBS or geographical breakdown structure. What is common for both of the systems is the system variant definition. So with one variant, with one configuration, we are going to drive both of the architectures. And here we are to start the video. So on the system or model-based system engineering CATIA Magic, we have two different configurations for the France and Japan. For the France, that was the baseline before. We see the heat exchanger that in this case is not needed anymore. We can move all of the objects from one configuration to another and adjust that for the Japanese market. Because of the heavy regulations that we had for the market, we had the additional equipment inside, making the evolution of that equipment and making a new configuration. We basically adjusted the design to the new market. We see here the relation between those new decisions and the relations between the systems that we built. Pushing in a new system configuration, we will later on see a little bit of changes on the completeness within the traceability that we have on the platform. The matrix that is in the background, it's really useful to identify the key takeaways, the key systems. And with system synthesis, system traceability, we see the connections in between the requirements and the objects that are on the platform. Just by picking a new object, in this case, a main header or intermediate header, we see the relation or impact between that item to be propagated on the rest of the items within the system. If there is something picked on the PNID side or PFD side, in this case, it will be highlighted in the 3D so that the user is also familiar with where that is stored in the 3D and what parameters are assigned to that object. If there is a new object being pushed inside because of the new configuration, then additional objects will appear on the system traceability and some additional links will be pushed from within. As we made a modification on the MBSE side, so pushing in different requirements, we also have different requirements on the PFD and the PNID. So the relation between the systems, within the System Explorer, we are opening the RFLP. RFLP, as mentioned before, is standing for requirements, functional, logical, and the physical, and creating or seeing, building the digital twin of our SMR. In this case, we have a 3D. Just hiding the building, we can see the rest of the cooling system that is located here. Every object has its own or can have its own space allocation. Space allocation can have its own requirements that are assigned to the project, and we can later on compare the items between the objects and the site if they're compatible. If there is a certain misalignment, we can get a report that the objects on the 3D are not aligned with the spaces, or 2D objects are not aligned with the 3D attributes, and then we can create or remodule the design. On the PFD side, that is stored here as the baseline. This was a PFD for the cooling system. So all of the objects and the line IDs are stored within a certain set of the catalogs. A certain simulation, or let's say a regulars check, can be performed throughout the design In this case, with the implement relation based on data in session, we can check if the object has its own 3D representation. In this way, it was graphical, but also the reports can be extracted out of that. Moving forward on the PNID side, so we are evolving PFD to the PNID, streams to the line IDs, PFD objects to the PNID objects. We see here a bit more detailed schema. So in this case, this will be our main point of focus. The zone with the two configurations. We pushed here additional third one for the LATAM because of certain humidity in the area that will have an environmental impact on our design, and we will need maybe to have a bigger heat exchangers, air coolers, or more powerful air coolers on the end to cool down the system if needed. Again, in this case, if we're talking about the PNID symbol, we see the connection between this PNID and the PFD symbol before, and we see the evolution of the PNID symbol to the 3D object. So following the entire life cycle of the cooling design. And again, moving back to the 3D part. So everything that's been built on the PNID side is now done on the 3D. And even if there is a certain set of simulation that needs to be pushed, we can perform a simulation based on the PNID or based on the 3D. In this case, simulation or making a configuration with different requirements for the Japanese market, different outputs, a different bill of material. So simulation based on the new regulations, new configuration. Simulation is based on the Daimler, so every equipment can have its own set of attributes. Engineering, non-engineering, the ones for the simulation. In this case, we are performing a simulation for the cooling system, and outputs of that simulation we are reusing for the later on requirements or new design, couple of iterations for the parts. All of the Modelica libraries are based on the PNID. If needed, some new ones can be created. New outputs can be added so that they fit the user needs, and a certain simulation is performed on top of it. Basically, this is covering, again, the entire life cycle of the SMR. So we saw the entering stage or conceptual stage with the MBSC, defining the key systems, relations between those systems, making evolution of that or a new configuration for the different markets. On the CATIA side, we saw the functional and the logical part, BFDs, PFDs, PNIDs, evolution of that on the 3D, creating a certain simulation on the 2D with the Daimola, and a certain simulation on the 3D with the Simulia. Outputs of that can be reused to define the new objects. And again, commissioning for the end, all of the objects within the space allocation for the maintenance, pushing in the documents for the maintenance, creating a regular maintenance for the equipment itself, and the exchange of information and the relations with the suppliers and the subcontractors, so everything can be traced on the platform itself. All of that is followed by supporting safety case demonstrations. So everything that is stored from within has a certain set of the documents which is following the objects, and therefore we can see and follow the maintenance and the maintenance activities of the key equipment within the plant. Thank you very much. That was all from my side. I hope you enjoyed the SMRs demo. So if you have some additional questions, feel free to ask. We'll be more than happy to answer all of them. Thank you.